Live from Frankfurt, Germany. This is Rational Science, and today we have our uninvited guest, and it's this gentleman. His name is Timo Weigand. Okay, he's a string theorist. And you might ask, who the hell is Timo Weigand, Bill? Don't you know? He's your employee. He works for you. Okay? You paid for his schooling. You paid for many of his travel expenses when he went to meetings and conferences and lectures. And now you're paying for his salary. Now, he works about half an hour away from here in Mainz. He works at this institute. And it's known as the Gutenberg University. Okay? And Gutenberg University receives lots of funds, I think all of its funds, from the government. You might say, well, Bill, I don't live in Germany. I don't have to pay for anything that Mr. Weigand does. Actually, there's Timo Weygands everywhere. You're paying for some of them in the United States. Other people pay for them in China and Russia and everywhere. That's one of the issues. The other issue is that all these people, they travel and they are invited into to conferences and so on. And sometimes, the receiving party pays for those trips because they want to hear what this fellow has to say or whatever. So one way or another, directly or indirectly, you're paying for their expenses, for their salaries, and even for their education before, they got a job. So the question is whether you're getting your money's worth, whether these people are worth your while. That's one of the issues you want to think about today, okay? And so let's find out in more detail who this man is. He's studied physics at Munich and Cambridge. He did his postdoc at University of Pennsylvania and also at SLAC, the Stanford Linear Accelerator, right? He later on apparently was a professor or did some work at Heidelberg University, here farther south here in Germany. He worked at CERN for a while, and today he's working at the Mainz Institute for Theoretical Physics. So he's been around. He knows his stuff very well, more or less like I talked about the other day about Maldacena. This fellow also is very well versed in string theory. Okay, so if you want to know something about string theory, well, this is one of those people whom you want to listen to. Okay. Okay. Here's the other half of his bio. It says, for many years, researchers have been searching for an all-encompassing theory of the universe that unites the four fundamental forces of nature known so far. While three of the four forces can be described uniformly, okay, using quantum theory, the fourth force, gravity, has persistently eluded these attempts so far. And they're referring to that thing on the upper left, which is known as the graviton, the particle of gravity. And they haven't been able to incorporate it within quantum mechanics, within the mathematics of quantum mechanics, okay? String theory is a promising approach to also represent gravity by means of a quantum model, okay? To develop a quantum gravity. And what they're referring to is they have gravity, or so they say they have, at the cosmic level, that's general relativity. Now they're trying to quantize that. In other words, they're trying to figure out some kind of equation from quantum that matches general relativity locally, okay? So that they can somehow put these two theories together that they don't talk to each other. General relativity with quantum mechanics. Regarding gravity, they don't talk to each other. So they're trying to merge them in some way, okay? That's the objective of string theory. And it says in the Prisma program where he works, he is one of the renowned experts in the field, no doubt about that. And they think string theory is an important cornerstone of theoretical research. Okay. Okay, let's find out. So what is this thing, string theory? I've never heard of it. Okay, let's find out what it is. And Mr. Weigand, he himself says a lot of this. He says, string theory describes the basic building blocks of matter, not as point-like particles, but as extended objects. Okay? In other words, what they're referring to here is that they're not going to go with a point particle of quantum mechanics. They're going to stretch that thing out and turn it into a line. So we can say the line particle, more or less. But it's really a little more subtle than that. I want to clarify that. You know, the point particle is not a point. It's not a dot like there, the two-dimensional dot. That's not what it is. And the string of string theory is not that rectangle, elongated rectangle, that has width and height. You know, as far as the eye can see, width and height at least. It could have a third dimension. No, they're not talking about that. They're talking about a one-dimensional line, just like in quantum you talk about a zero-dimensional particle. So what are they talking about? Right there now we have to clarify that. Well, in quantum mechanics, the zero-dimensional particle is actually a location, the point of geometry, which represents a location. So they've said they can never define the word point or the word line. Very easy, very, very easy. If a dot is the point, very clear. You point to it and say point, and that's what you pointed to a dot. But if the dot is something else, then it's not a point. So what is a point? Well, the point is a location. And of course, a location doesn't have dimensions like width and height. Location is a dimensional concept. And so if that's what a particle is, a location, well, then what is a line? Well, in other words, of string theory. Well, what they've done is they see the so-called line of string theory is an itinerary. It's a trajectory. It's motion. It's made of not points, not dots. It's made of locations. So we should get rid of the word point because it confuses people, because people think they're talking about dots and lines. No, that's not what they're talking about. They're talking about locations and itineraries. That's why they're so-called lines, the ones that underlie string theory, are one-dimensional. Because what they're saying is it really has no dimensions. What they have is a number line. And the number line represents locations. And they give numbers to each one of those locations so they know how far away. They're interested in how far away you are from a given point, from a frame of reference or whatever. So let's get that straight. We have this line, which is not a line, it's an itinerary. And that's, you know, the geodesics, another itinerary, the shortest distance on a curve, and so on. So we're talking about itineraries. That's the first thing. This one, graviton, is a closed loop itinerary. It's a circle. You can think of it as a circle. Maybe that's the best way to imagine it. Okay, so you have a closed loop itinerary, trajectory, motion, right? We're not talking about the moon here. We're not talking about a physical object. We're talking about motion. And they claim that this motion vibrates. You know, the vibrations of this motion is the graviton. Okay? So I hope you got that straight. So the graviton is zero-dimensional, made out of a one-dimensional vibrating motion. Okay, this is how why? Because all equations can only describe motion. That's the only purpose of an equation. Any equation. Equation, it's a description of motion. Like I like to say, mathematics completely, all of it. The whole discipline known language, it's not even a discipline, it's called the language. The whole language of mathematics is a language of quantitative adverbs. That's all that mathematics is, quantitative adverbs. There's nothing else. There's no static concept, because whatever static concept you have, like distance, it's measured. It's measured with what? With unrolling the measuring tape or with a clock or whatever. And so there's a dynamic component to that underlies that measurement. So all measurements are dynamic. So in physics, we have something different. Distance is separation between two objects, between the table and the chair. We don't care how much, we just recognize that there is a separation, period. That's not what it is in math. In math, you unroll the measuring tape and say, how much, how far away is the table from the chair, or vice versa. Okay, so let's keep all that in mind. That's the context. At the beginning, these were often illustrated as threads, strings, and again, they're not strings, and gave the theory its name. Okay, yeah, it should be called itineraries or geodesics or whatever you want to call them, except anything which is structural. You should not call them lines or strings or ropes or cables. That's not what these are. These are descriptions, mathematical descriptions, adverbs, quantitative adverbs of itineraries, of motion, of behavior. Okay? So that's the first thing you need to, that's the overall picture. Furthermore, string theory envisages the existence of a 10-dimensional space-time. Oh my God. So we have the 4-dimensional so-called tesseract, okay, and nobody can imagine that because what you're staring at there is really two nested cubes. You know, a nested cube, one inside the other, and they put it in motion. And that's supposedly the time dimension, we can call it that. No, it's a number line. So what they have is something moving inside a cube, one cube inside the other cube. They call that 4 dimensions. It's not. It's a 3-dimensional nested pair of nested cubes, and they're in motion, okay? And they call that 4-dimensional. It's really 3-dimensional motion, 3-dimensional object moving. That's all that is. And the question is, how can you imagine 10 dimensions? Is it like I show there? Is that what they have in mind? I mean, what are they talking about when they say 10 dimensions? Okay, so they clarify that. Here it is. You get an idea of what he's talking about here. He says, in order to derive statements about physics in a lower energy range from string theory, or to make them experimentally verifiable in this way, physicists have to formulate further assumptions and develop models. Okay, models. I like models, no problem. How else would it be? This is a direct statement. How else would it be possible to explain that string theory in its mathematical description assumes a 10-dimensional space, but our observable environment has only 4 dimensions, 3 spatial and 1 temporal, is how Timo Weigand describes the challenge. Okay, that's in the Prima site where he works. And so the question is, first he's talking about description. Second, he's talking about experimentally verifiable. Verifiable by whom? By the Pope? I mean, who's going to verify this thing? In other words, verifiable has to do with proof, with evidence, with convincing someone, with persuading someone to change his mind. That's what verifiable means. In science, we don't do verification. That's what they do in religion because they're trying to convince, persuade people. They're trying to get to recruit. In science, all we have to do is explain objectively so that we can understand the mechanism that you propose. And again, a description is not science. Description, I can describe a chair, and that doesn't mean that I know that I'm a scientist. No, a description is not. What you need is an explanation. You need to explain how this universe works. You need to explain how gravity works. I thought that was the goal, at least, right? Anyways, he continues, the solution that he proposes is that 6 of the 10 dimensions are combined into a compact unit that exists in addition to the known dimensions. In string theory, this is called compactification. So they're going to compact or compactify 6 of the dimensions because they can't account for them. They claim they can account for 4 of them, but not for the other 6. And again, he says it there. He says, how else would it be possible to explain that string theory is, in its mathematical description, assumes a 10-dimensional space? Yeah, how can you? I mean, obviously you're not talking about physics. You're talking about some imaginary world that you have in your head and that you're going to describe with mathematics, but you're not going to be able to even to describe it physically, or make a model of it. How can you make a model of a physical model of this 10-dimensional world that you're thinking of? What is this? Is this real? Or what are we talking about? How can there be 10 mutually perpendicular directions? We can only imagine 3 of them. So, the universe is 3-dimensional as far as matter is concerned. Everything is 3-dimensional. I don't know where he gets the 4th dimension. Maybe he works in a different planet and he sees a 4th dimension perpendicular to all those 3. And yeah, it's like Stephen Hawking says he cannot imagine this 4-dimensional world that they've created in mathematics, much less can they imagine this 10-dimensional world, this 10-dimensional space. So I don't know how they're going to do an experimental verification of that. Okay, let's continue. The solution, he says, 6 of the 10 dimensions are combined into a compact unit. Okay. And among other things, Tim Weigand's research focuses on describing this phenomenon physically and mathematically. Again, he won't be able to describe it or explain it or verify it or do an experiment physically because it's beyond hope. He cannot even imagine, he cannot visualize it, much less can he do an experiment. I mean, the way it works is that if you're ever going to do an experiment, the first thing you have to do is design it. It's called design of experiment. We used to shorten it to DOE, design of experiment. Then you can do an experiment. Otherwise, the manager will not approve the money because you haven't visualized what you're trying to accomplish. So the first thing you have to design it means you got to write it up. And maybe you give a presentation and say, look, this is what I intend to do. Fine, no problem. Then people can understand what you're going to be doing, okay? But these people are saying, we can't imagine this 10-dimensional universe, this 10-dimensional space, okay? Yeah, neither can I. And so then what are you talking about? And they want to verify it experimentally. You figure it out. I mean, I don't know what they're doing. And so again, the question is whether this is worth your money. You're paying for this guy's salary, okay? Keep that in mind. And for his travel expenses, for his schooling. Question was, it worth it? Okay? Did you get your money's worth? Okay, so he continues here. He says the following. He says, all in all, string theory provides us with a controlled and calculable framework to study quantum gravity. Okay, framework. Okay, I don't know what studying is not enough. You need to produce results. Everybody can study and not pass the test. No, you got to pass the test if you're gonna give me my money back in some way. If I'm paying for your schooling, for your travel expenses, for your salary, I want something back. What are you going to give me back? Saying that you just studied? Is that it? Both from a theoretical perspective and with regards to the possibly far-reaching implications for the description of physics at lower energies. Again, a lot of descriptions. I want an explanation. I don't hear the word explanation there. At the same time, it opens surprising and deep connections with mathematics. Irrelevant. These can also be used to test general ideas about the structure of quantum gravity via string theory. Okay, yeah, we want to know the structure of gravity. I mean, when we talk about structure, hopefully we're talking about a thing. Okay. So, yeah, everybody wants to know what the structure of gravity is. What causes gravity? That's what we're after, yeah. So I think we're on the same wavelength there. His conclusion, okay, the fundamental question for a unified theory of all forces of nature in the context of string theory has already led to fascinating relations between quantum gravity in general, black hole physics, and the geometry of string compactification spaces. And there you see an example of each. We have the quantum gravity is represented by the graviton, the black hole, famous black hole. They claim they took a picture of it. There you see that's the representative of general relativity. And then you have this compactification of spaces, which is what string theory apparently is trying to elucidate. You know, these six, really seven, because I don't know where the fourth dimension is, but I've never seen it. I would like someone to draw it for me, you know, 90 degree to the other two, to length, width, and height. I'd love to see that. But they say that they're missing six dimensions. They don't know where they went. Okay, so find them and then come back. Okay, please find the six dimensions that go 90 degrees to the other three. Okay, so that we know what you're talking about. Please draw it. Please bring it to the conference. Okay, next time. Otherwise, don't talk about it. I mean, what is it worth to talk about something that has no possibility of even being imagined? Okay, so Mr. Timo Weigand, he wrote a few papers, and I framed something that he said. He said this, I think, 2011. He says, "We are string theorists, okay? We want to understand what's out there." Hey, totally in agreement. I want to understand what's out there. What is out there? So we need to know what a what is, what an it is. Hopefully we're talking about something real, you know, something that's out there, okay, outside of us. And that means that if we're going to talk about gravity, we need to find out what causes gravity, how Mother Nature does that magic trick of, you know, very simple. You let go of the pencil, okay, and it falls to the floor. We're done. That's the only experiment we need. We verified it. Okay, we verified gravity. What is gravity? The pencil falls to the floor, always. Never falls to the ceiling. We're done. We did all the experiments we ever need to do to understand gravity. The description of gravity. We're done. Now we need to understand it. Now we need to find out what's causing that. Okay, and hopefully that's what he's referring to when he says what's out there. So he writes all these papers here. You have quantum corrections in 4D, n equal 1, infinite distance limits, and the weak gravity conjecture. Whoa. All this to understand why a pencil fell to the floor? Supersymmetric protection in the swampland. Okay, maybe this pencil fell into the swamp. Okay, fine. Quasi-Jacobi forms, elliptic genera, and strings in 4 dimensions. Strings in 4 dimensions. Emergent strings from infinite distance limits, and so on. You know, I mean, okay, what is he talking about? Yeah, and here I pulled some of the jargon only from the first paper. This is just from the abstract in his first paper up there, okay? And this is some of the terms that you need to know in order to understand string theory. 4-dimensional theories, supersymmetry, decompactification, weakly coupled perturbative, gauge threshold, renormalization, infinite distance limits, sublattice of states, and so on. So what was the purpose of all this, of this paper? I mean, was it to figure out how gravity works? And the purpose is right there at the bottom. We predict how the masses of this tower must be renormalized in order for the weak gravity conjecture to hold at the quantum level. What is all that about? What is this the goal? Is this the design of experiment? This is the experiment he's going to run somewhere in a lab and show this stuff? Is that the goal? Is that the purpose? I don't know. Unless you understand it, you know. And again, there's only 5 people in the world that understand that language, that jargon. I mean, who was it? Einstein, and later on Feynman said the same thing, more or less. Says, you know, if you can't explain it to a barmaid, and the other guy said, if you can't explain it to a 10-year-old, well, you don't know it well enough. Okay, I don't know if they said it, but I like those statements. Yeah, if you can't explain it to a kid, you know, how gravity works, why this pencil falls to the floor, which is what we're trying to figure out here, right? We're trying to figure out gravity, how gravity works, hopefully. I mean, he said he wants to know what's out there, okay? So I want to know what's out there, like what's here or here. I mean, if there's something pushing or if there's something pulling. That's what I want to figure out, right? Because this pencil falls to the center of the earth. And I'm sure he won't deny that. And so the question is, how does Mother Nature do that experiment, that trick, that magic trick? She does it with nothing, with concepts, with mass, concept mass, with the concept energy. She does it with a concept field, with a concept charge. All these are mathematical concepts. I can't pull or push with a concept. No, I need a physical object. You need to identify the invisible, intangible, right? Physical object that is in touch with the skin of the pen. That's the objective, not what Mr. Weigand just mentioned there, whatever it was. Okay, I forget it already. Okay, he continues. Oh no, what I want to show here is that these are the questions that people ask. Like in Quora, you go to Quora, they ask, what is gravity? That's what people want to know. They don't want an equation. They don't want you saying, well, look, let me take the derivative and then calculate the, I don't know, the integral. They don't want that. They don't understand any of that. 99.99% people on the percent of the people on the earth, they don't know anything about math, and they could care less about math. No, they want, just tell me why this pen falls to the floor. Yesterday I dropped a baby. He fell on the floor. Why did he fall on the floor? I mean, what caused him to fall on the floor? Why didn't he stay in my arms? Why didn't he fly upwards? No, he always falls to the floor. That's what the people want to know. And so they ask these questions. How does gravity attract materials? What causes gravity? Do matter's properties have anything to do with gravity? How does gravity work? Why do we know what causes gravity? Why is there gravity? And it would be nice, if Mr. Weigand would go into Quora and answer some of these questions. I mean, he's an expert in gravity, right? Or trying to be. Be nice if he could answer some of these questions. This is what people want to know. People don't want you to just give them an equation and say, oh, here's the equation. No, people want an explanation. And these people are giving them equations, description, and then idiotic, irrational poppycock. The mechanisms they have for gravity are laughable. And it'd be nice if you could also answer, by what physical mechanism does a magnet attract another? I mean, here we have, two magnets, okay? And, everybody who's played with magnets realizes that there's already a pull there. It's pulling on me, from the inside. Nothing's pushing on my hands. It's always from the inside. So there's something there, something we can't see or touch, but there is something there. Or as Mr. Faraday said, lines of force, those are real. There's something real in there. And Maxwell said there is matter in motion. He was referring to some kind of exotic matter that we can't see or touch, but there is something in motion in that region we call field. That's what you got to identify, not just use the word field. Word field doesn't tell us anything. In fact, it hides more than it tells us. We need to identify what comprises the field. That's the object you need to identify. And since this man is an expert, Mr. Weigand, it'd be nice if he would go to Quora and answer some of these questions. Okay? And the other one at the bottom also, by what physical mechanism does an electron remain bound to a proton? I mean, he's an expert in quantum mechanics. Yeah, just tell me why the electron doesn't fly away spontaneously when it's in a normal state. Hydrogen is a normal state, right? Okay, why doesn't the electron just fly away? What keeps it bound to the nucleus? I mean, these are simple questions that I'm sure he would be able to answer. Or does Mr. Weigand believe in this? Does he still do quantum mechanics with this, with transverse 2D waves? Does he use magical quantum particles for light? Is that how he mediates light? And if so, how does he mediate gravity? Like, is he going to use also gravitons? How do they pull? If they're coming out one way, how is it that they pull? Is that his planetary atom? Is that the one he's going to use for current, for electricity, right at the bottom? Okay. So these are the questions he's got to answer. Are these his foundations for string theory? Because he's going to use quantum as a foundation for string theory, which he's going to later on somehow merge with general relativity gravity, right? The warping of space-time. So if this is his quantum foundations, first he's got to tell me this. He's got to say, okay, what is light? What is gravity? What are you going to use as a simulator for, especially for gravity? That's what he's trying to explain. What does your atom look like? How does an atom shoot a graviton in another atom. Okay, fine. How does it attract it if it's shooting a graviton? Okay, and if he says, well, that's not my quantum atom, well, how do you explain electricity if that's not your, if the planetary model that Bohr and Rutherford invented, if that's not your atom, please explain electricity. What is electricity? Isn't it the flow of beads from one atom to another? That means that is your atom. You are using the quantum atom. So that's where he's got to start. He's got to have an atom to begin with. If he doesn't have an atom, he can't give his physical interpretation. He cannot explain gravity, let alone light or anything else. So I don't know what he's trying to accomplish here. This is where he's got to do the work, not in a bunch of math saying, oh, look, I've got all these equations, I've got all these derivatives and integrals. Yeah, and please tell me how gravity works. That's what people want to know. And we don't have to go to Mr. Weigand. We can go over his head. We can go through someone a little more important than him, someone who won a Nobel Prize. I mean, if you're into, into authority, this is one of the men to go to, okay? And what did he say? I think I can safely say that nobody understands quantum mechanics. And he says, do not keep asking yourself if you can possibly avoid it. But how can it be like that? Nobody knows how it can be like that. This is a Nobel Prize talking to you, okay? From Ultratum, from the ground, okay? Nobody knows how it can be like that. The more you see how strangely nature behaves, the harder it is to make a model that explains how even the simplest phenomena actually work. So theoretical physics has given up on that. So if theoretical physics, meaning quantum mechanics, has given up on that, on trying to explain phenomena, natural phenomena, what is Mr. Weigand up to? What is he trying to do? We need an explanation. And here Mr. Feynman says that they cannot explain it. And of course, Mr. Feynman could not explain it because he was using waves and particles. That's why he could not explain it. He had an irrational starting point. He had an irrational hypothesis, proposal to begin with. You cannot explain Mother Nature's workings with waves or particles, and that's why they ended up with irrational explanations. That's why they cannot explain the invisible world out there, how Mother Nature does her things. That's where the problem is. And here we have another gentleman. He's still alive, okay, and his name is Susskind, Leonard Susskind. He's from Stanford, and he says modern science is difficult and often counterintuitive. Well, only if you're a mechanic. If you do it with particles or waves, then it's counterintuitive. Where intuition and common sense failed, they had to create new forms of intuition. New forms of intuition. Mainly through the use of abstract mathematics. I don't know what that helps, okay? But when common sense fails, uncommon sense must be created. So they have uncommon sense in mathematics, okay? Human cognition does not operate according to principles of common sense. Mr. Susskind is saying that Father Universe does not agree with our way of thinking here, us humans, because he runs the universe in such a way that we cannot understand it, and all we can do is through mathematics more or less describe it and forget about explaining it, like Mr. Feynman just said. And here's another statement from Mr. Susskind, just in case, okay? And he doubles up on that, and he says the following. He says, you and I evolved in a world of 3 dimensions. Yeah, true. We can't visualize more dimensions. I can visualize 3 dimensions in my head, but I use X, Y, and Z to describe them mathematically. Okay, fine, you describe them with X, Y, and Z, no problem. Now I go to 4 dimensions or 5 dimensions. I can't visualize them anymore. I can't say now, close your eyes and view in your head 5 dimensions, because I can't do it either. So we're stuck needing mathematics because evolution didn't equip us to be able to visualize quantum mechanics. It didn't equip us to visualize 11-dimensional spacetimes. Evolution did this to us. So once again, I ask, what is Mr. Weigand trying to do? We have more senior members. In fact, Susskind is a string theorist. And these people are saying, you forget about quantum mechanics, forget about visualizing any of this, forget about even imagining this, because you cannot imagine. That's why you can't draw it. You can't make a picture of it. In fact, you go to any of these papers that this individual wrote and you won't find a single picture. And so the question is, he's saying he's going to produce experimental evidence to try to verify something. How are you going to verify something like gravity, which is invisible and intangible? And more yet, how can you visualize it when you simulate them with particles, with discrete particles, one-way particles, particles that only travel one direction? And with that, you're supposed to produce the attraction of gravity. What is Mr. Weigand trying to do? I mean, he can do all the calculations he wants. What does it help us? And so let me give you a little for instance here, a little example. Okay, this is the famous black hole that they found out there. This is a black hole, right? And that you say, well, what is a black hole? And they'll tell you, well, it's a star that had so much mass, a lot of mass, much more than our sun, and it collapsed because of its own gravity to a point where at some point it exploded and left behind, just got rid of its skin, so to speak. And what left behind, something that kept shrinking because of the enormous mass. You had all these very heavy elements comprising that little ball. It just kept shrinking, 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 shrinking until it was no more. No volume, no radius, no diameter, no size, no nothing. Okay? Now, a lot of people don't understand that. People say, well, no, black hole never goes to nothing. Because if they said that, a lot of people would question that, right? So they say, no, it just becomes very tiny, unimaginably small, infinitesimally small, okay? That's the way they put it to you. Well, so this is how the black hole is created here. You can see it. It's what's left behind is this thingy there, this little ball, and supposedly not even the ball remains because that's supposed to be just a singularity to which this entire mass collapsed to. Okay? So that's essentially what it looks like, or the notion that they want to give you, and the picture here that supposedly they let's hold it. Where is it? Here. This picture, it just gives you an idea of what they're thinking of. They're saying that's a black hole. Okay? That's what it should look like. And that's the picture supposedly that they took a picture of a couple of years ago and got a Nobel Prize for. Okay. Turns out that, again, the black hole is zero-dimensional. It collapses to zero size. And here are a couple testimonies. Okay, the black hole radius is 0, which means its density is infinite. And all these are professors, they're all PhDs saying this, okay? So this is what they learned in college. You can agree with them or disagree with them. I'm just saying there's a lot of people out there, professionals, who actually believe, black hole is zero-dimensional, and they just repeat it. They never ponder what they're saying. I mean, how can it be zero-dimensional? What are you talking about then? Black holes are the evolutionary endpoints of stars at least 10 to 15 times as massive as the sun. If a star that massive or larger undergoes a supernova explosion, it may leave behind a fairly massive burned-out stellar remnant. With no outward forces to oppose gravitational forces, the remnant will collapse in on itself. The star eventually collapses to what? To the point of zero volume and infinite density, okay? Creating what is known as a singularity. That's from NASA, okay? That's from their site. Now, we're talking about professors, we're talking about an institution here, okay? More evidence, you need more evidence, you're not convinced yet? Okay, here it is. Let's put it over here. Here's another one. It says, what is a black hole? Is it big? Is it humongous in size? No, it's zero-dimensional. 0D, no dimensions, no size, no radius, no diameter. In theory, it's not the size of a pinhead, but actually has zero size, a true mathematical point. professor who teaches this at Ohio State. A collapsing stellar core with n mass greater than 3, the sun will become a black hole. Okay. If the initial mass of a star is greater than 20 mass of the sun or so, la la la. Since it is too massive to become a neutron star, the dense core collapses totally. Okay? Nothing can stop its infall. According to the laws of physics taken to their logical conclusion, it becomes a singularity. What is a singularity? Singularity is a point which has 0 radius and infinite density. Fortunately for the sanity of astronomers, it is impossible to see a singularity. No kidding. We're talking about nothing. That's what these people are talking about. They're saying there is a nothing out there, a non-existent structure, and they call that a singularity, and that's the heart of the black hole. So, and that's what Mr. Weigand studies, or plans to somehow merge with the quantum mechanics that he cannot even justify the foundations of. You know, what is light, what is gravity, what does an atom look like, what is electricity. He cannot, what is magnetism. You know, he cannot justify any of those. He's already gone past that. He said, oh, that was high school, what they call gymnasium here. No, he's further on. Now he's up there, he's talking about string theory. Well, you should come back to high school and explain it to the high schoolers. Okay. And it's okay, so we need more authority maybe. Let's put some authority here. I mean, you're not going to get more authority than Stephen Hawking. And he says that Chandrasekhar got a Nobel Prize for what? For showing that a black hole could collapse, which is big enough, would collapse to 0 size. And Eddington was the supervisor of Chandrasekhar while he was studying in England. And Eddington thought it was simply not possible that a star could collapse to a point. Einstein himself wrote a paper in which he claimed that stars would not shrink to what? 0 size. And then, and this is all in his book, A Brief History of Time, Hawking says, however, he was awarded the Nobel Prize in 1983 for his early work on limiting mass of cold stars. Chandrasekhar had shown that the exclusion principle could not halt the collapse of a star more massive than the Chandrasekhar limit. Okay, still unconvinced? Well, there's one more here, and this is another Indian fellow. And he's a very important fellow over there in India, and he says the following. Let me just put this up. Let me get this right. And he says the following, okay? He says, on solving the equation with a particular value rho of central density, you will get a model of a star with mass m and radius r. Plot r as a function of m and show that r falls to 0 when m is equal to the Chandrasekhar mass. R, radius, goes to 0, right? If you can do all these, then you have repeated the calculation for which Chandrasekhar won the Nobel Prize. So we have Mr. Chandrasekhar, and he won the Nobel Prize for proving that black holes are 0-dimensional, can be, at least. If the star is big enough, it can... it'll shrink to the point where it's got 0 dimensions. So a lot of people do not understand that. They think that's nonsense, and they say that's not a black hole. A black hole is more than 0-dimensional because, as you saw in the picture, it's got this black circle in there, and they say, well, that's more than 0 dimensions, so obviously a black hole is not 0 dimensions. But these people are all telling you it's 0 dimensions. Singularity is 0 dimensions. It collapsed to nothing. All structure has been crushed out of existence, and all that remains is a mathematical singularity. Mathematical singularities don't have radius, don't have size, don't have diameter, don't have volume. There's nothing there. It's just all mass. Infinite mass because there's no volume. And according to the equation, you know, you have infinite mass, because there is, you know, there's no volume. Okay. Here's another testimony that reinforces that. These people are also professors. Okay, just so you know that I'm not I'm pulling their words here, okay? And they all say the same thing, that a black hole crushes matter. All matter that falls into a black hole crushes it out of existence. There you see it, crushed out of existence everywhere. Okay, so black hole, there's nothing there, absolutely nothing there. Because any structure, any atom that went in there, any particle that fell in there was crushed out of existence. There is no structure. It's only mass. That's the only property aside from, well, charge and angular momentum. But forgetting about that, all black holes, all of them have mass. That's it. And what is mass? The quantity of matter, and the black hole has crushed all matter out of existence. So I don't even know if it has mass, because mass is the quantity of matter, or a measure of the quantity of matter, which has now been crushed out of existence. All we have is a mathematical number, calculation. That's all that is contained within a black hole. And even if we grant that, let's say that it's got tons of mass, tons of kilograms, no problem. How does that mass pull on a star far away and force it to go around itself? I mean, you got to explain that mechanism also. It's not enough to say, oh, it's mass. Well, yeah, so what is the mechanism? Are you going to do the warp space canvas, the fishnet? Is that the mechanism? Okay. And to top it off, we get a definition of what a black hole is. Okay, here it is. What is a black hole? It's a region. That's what it is. It's a region. Region is a concept. The region of your hand, the palm is a region of your hand. China is a region of the planet. Okay? So region is always of something else. And in this case, black hole supposedly is a region of space-time, or of space. So region is a concept. It's not a physical object that you can hold in your hand or touch or anything like that. No. This is a mathematical concept, and it's known as a region because in that region something happens. That's all they know. That's how vague the definition of a black hole is. And so that's an abstract concept lacking body or size. Of course, that's why it has no volume, no size, no anything. No concept has size. I mean, love, what is the size of love? I mean, is it 2 centimeters? I don't know, Some have longer love, bigger diameters of love. A black hole is not a tangible object, but a region in space. Max Planck Institute. Okay? And a black hole is a region. One seems to land in paradoxes if one thinks of them as things. It's not a thing. It is therefore problematic to think of the singularity as having location. Obviously, if it's not a thing, it cannot have location. Concepts don't have location. He wrote that in 2009. He modified that in 2019 for the Stanford Encyclopedia of Philosophy. Now he says the following. He says, black holes, although they are nothing more than regions, appear to become the thermodynamical entities with a temperature and an entropy, blah, 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 blah. One runs into difficulties if one tries to define singularities as things that have locations. Yeah, you can't have location unless you have a thing. You need location. You need a thing to have location or motion. There is no such thing as motion without a thing. There's no such thing as location without a thing. You need the thing. What these people do is they remove the thing, they replace it with a dot. They call a point, which is zero-dimensional, which is not really a dot, which is not a point, which is really a location. Location of what? Maybe of the center of mass or the center of charge or whatever of the object that you're dealing with. So they forget about the object. They throw it away and they say, we're just going to deal with the charge or the mass or whatever. So they talk about kilograms. They don't talk about objects. And here's another testimony as far as region. There you see it. That's what a black hole is. It's a region of space. That's it. So we're talking about a region. So what you're staring at is not a thing. I mean, a hole. If you don't have the ground, like Bugs Bunny wants to get inside the hole, he's got to have ground. The hole is in the ground. You have to identify the ground. In this case, you can say space. If you treat space as a physical object, and what? You created a hole in space? You ripped it? So this is surrealistic at this point. Okay, so here it is. Let me give you this this analogy so that you can take it to the bank with you. Okay, here's your famous black hole. Okay, this is where we start. We're going to replace this black hole just to show what Mr. Weigand does. Okay, we're going to replace it with this. We're going to replace it with heaven. Okay, so now we had a black hole. We're going to replace the black hole with heaven. And here we have the graviton, okay, which is the string version of the graviton. And what we're going to do is we're going to replace it with this. We're going to replace it with the soul going to heaven. Okay? And let me tell you where I'm going with all this. Okay? Where am I going? I'm saying that, you know, and you can create also, by the way, you could create, just like Mr. Wygand did, we can create, you know, fancy language to talk about all this. You know, we can say, you know, transubstantiation or some fancy word like that, which 5 people in the world maybe know about, and that's it. You know, and nobody after that can follow them because these people speak their own language there. And you say, Bill, why are you using this in an analogy? Okay, let me show you why. Let me show you why, because we're trying to figure out what Mr. Weigand is doing and whether he's worth your while, whether he's, you know, if you really want to contribute to his further studies, okay? Or if people who work in string theory in general. Okay, so here's Mr. Weigand. He says, look, I've calculated, you know, how fast a person can go into heaven. I calculated a derivative that shows you, you know, it's a change in one parameter with respect to another. Okay, or he can say, look, I've got the integral for heaven. I can tell you what the surface or what the area or the volume of heaven is because I've calculated it. Okay, so he gives you some fancy equation there, and he says, look, this is what I'm working on. And you say, well, Timo, but I don't think souls go to heaven, and I don't think there is a heaven. I don't even think there is a God. And so here you tell me that you're making all these equations to calculate how a soul goes to heaven or what the size of heaven is, and you're going to calculate, you know, what happens at the edge of heaven and when the soul crosses the boundary into heaven. And I mean, are we talking something real here? I mean, I don't think there is a soul that flies to heaven. I don't think there is a heaven. I don't think there is a God out there. And he says, you don't believe in God? You don't believe in heaven? My God, where have you been all these years? Everybody believes in God. Everybody believes in heaven. Who the hell are you, Bill? I mean, to question the existence of God, where did you get that? And I'm saying, well, where did you get God? I mean, where did you figure out that there is a heaven and that there is a soul that goes to heaven? Okay? And he might say, well, I got it from a Nobel Prize winner. In fact, he won the Nobel Prize this year. Okay? That's this gentleman here, if I can find him here. His name is Mr. Reinhard Genzel. In fact, I wrote about him in the past, wrote a paper on him. The outstanding main result of our work, this fellow works for the Max Planck Institute. He's one of the head honchos there. The outstanding main result of our work is the proof of existence of an astrophysical, I modified it a little bit, I've edited his paper, I hope he doesn't mind, okay, of an astrophysical heaven beyond any reasonable doubt. An unambiguous proof of the existence of heaven as defined by general relativity requires the determination of the gravitational potential to the scale of the event horizon. This proof can in principle be obtained from spatially resolved measurements of the motion of test spirits in close orbit around the nucleus. Okay? In practice, it is not possible yet to probe the scale of an event horizon of any heaven candidate with spatially resolved dynamical measurements. A more modest goal then is to show that the gravitational potential of a galaxy nucleus is dominated by a compact non-stellar mass, and that this central mass concentration cannot be anything but heaven. Okay, that's what Mr. Genzel won the Nobel Prize for this year. He proved the existence of black holes, and he proved it indirectly. He says, look, what else could it be? I mean, it's, that's his conclusion. Where did he get this? I mean, where does all this come from? Because he wrote this many years later after someone allegedly, okay, discovered the first black hole. And that was Mr. Tom Bolton. He's given credit for that. I think he's Canadian. And Mr. Bolton found this. He was looking at a region of space called Cygnus X1, the Swan, and he found a star there. And he says it's moving around, okay, but the star is orbiting around nothing. And he calculated the orbit, the distance, all this stuff. He said, oh, I know what happened here. There's a black hole somewhere in between there, and he put it in there by hand. He said, there's the black hole. Okay, so this is how he visualized that. And since then, in the 1970s, just about everyone, accepted that black holes were real. And then Mr. Genzel comes a couple decades later and says, oh, we've proven the existence of black hole. What else could it be? So this is their proof. Their proof is, the curtain moves, and you say, well, what else could it be? It's got to be the spirit of my grandmother. Well, maybe if you close the window, maybe it stops moving. But by then, I guess grandma went through the window, went back to heaven, Yeah, the issue is that the only explanation for why a star moves? Okay. And so let's find out if we can do better. Oh, there's one other issue here before I go to this. Another issue that they say is that they found that gases from a star are sucked in by. There you see the black hole, but they see nothing in there. But they say, what else could it be except the black hole sucking in all this gas from a star, okay, from the surface of a star? It just goes to nowhere. And so they say, well, that nowhere is a black hole. So it's not only that a star revolves around nothing, but also that the skin of a star is being sucked up by something in there. And they don't know what it is because they can't see anything in there. And they say, well, the only thing that can do that is a black hole. Okay, so that's their reasoning. It's always indirectly. Okay, they never saw a black hole, touched a black hole, none of that. They go in there and they look and they say, well, what else could it be? That's their reasoning. Okay, well, let's find out what else it could be. Let's show them what we can do here on Earth to show that there is another mechanism. Here you see one of them. You put a charged ball in a magnetic field, and it'll go around in circles, just like a star does. Okay? So it's not only through black holes that you can create this effect, you can do it also with a magnetic field coming down a charged ball. And here you see the gas version, okay? You can see smoke being sucked up by a rotating magnetic field. Okay, so they have this magnetic field, and it just sucks up the smoke, which is a gas, particles there, right? So we don't need a black hole to explain what happens out there in space. We can do it with a magnetic field, whatever a magnetic field is. Right now we're not going to get into that, okay? But whatever a magnetic field is, it can produce these same effects, and it can do it out there in space, in the cosmos. So here, let me show you a different version of the so-called black hole. And we start with a galaxy, okay? Here's a galaxy, okay? And you can see it rotating, okay? Now what we don't see is the magnetic field of the galaxy. So let's see if we can put that in there, okay? Here it is, the magnetic field of the galaxy. In rational science, we do that with threads, okay? But right now we're not going to get into that. And okay, and so let's look at why a star would be moving around in circles. Okay, there you see the little star at the bottom, almost in the center there, that's moving around. And right at the upper left-hand corner, you see what I showed earlier, the little ball in the magnetic field. So if the magnetic field of the galaxy is coming down about on this charged object. You know, it's got magnetic field, that little star there. And so if it primarily is strong in that region of the galaxy, the magnetic field, then it would do this. It would do exactly what you're seeing there. It would move it around nothing. Not because it's moving around a center that's got a lot of mass, but because you have a magnetic field bearing down on this charged object. Okay? And then how about the smoke? Same thing here. Here we get the gases from a star. Okay, and again you can see it there. If you see that the gases from the skin of a star are being sucked up by nothing, well, that just as well can be done by what you see there. It's done by a magnetic field that can just as well skin a star alive, so to speak. Okay. So we can produce this in the cosmic scenario without any black holes. We do not need black holes to explain these phenomena. We have another explanation for that. And of course, for that, you have to change your assumptions. That's what you need to do. And Mr. Weigand has no assumptions anyways. He's relying on the assumptions of quantum mechanics, which are irrational. We haven't been able to explain anything in the last 10,000 years, a single phenomena of the invisible world of Mother Nature's with either particles or with transverse waves. Waves we've only had for 400 years. But waves and transverse waves and particles, neither one can explain the invisible world of Mother Nature. Okay? And so that's where we have to change the assumptions. So what do we change? Well, here it is, closing arguments here. First one is that what do I want to show here? No, let me just skip that one. Otherwise, it's going to be too long. These are the assumptions that need to be changed by the people who do quantum mechanics. Okay, they should stop doing particles. They should stop doing waves. And what do we propose instead? Well, we propose that all atoms in the universe are physically interconnected. We don't have a sandbox. We don't have a beehive with all the bees buzzing around. We don't have individual discrete entities. What we have is all atoms in the universe are physically interconnected. What interconnects them? Well, what interconnects them is the mediator of light, which looks wrong again, which looks more or less like this. They're so far at the bottom, I got to pull them all the way up. Okay, it looks more or less like this. Okay, we have a single thread in the entire universe that constitutes all the matter. Okay, and this thread turns into all these atoms that are buzzing around us. We're made of them as well. That's all we have, a single thread in the universe, and it coils around itself and produces, you know, the electromagnetic ropes that bind every atom. In fact, every atom is made of the same threads that comprise the ropes that interconnect them. So there's a single thread in the entire universe, and it's a new model. And with that, we can explain, you know, gravity. We can explain physically. We give you a physical interpretation. We give you a picture, something you can sink your teeth into, something you can understand just by watching the pictures, because it's a realistic model. We just need to abandon the particle and wave models. That's it. But what we're talking about, we can explain, you know, magnetism, gravity, the behavior of light, electricity, the behavior of the atom, etc. All the invisible stuff, which quantum right now cannot explain. As Mr. Feynman just said, no one can figure that out. Yeah, under particles, you can't figure it out. You need to change the hypothesis. Instead of applying Popperian falsifiability where they needed it, they didn't. That's where they did not apply Popperian falsifiability. Here was the lost opportunity. They should have said, well, hold it, we can't explain a single experiment. All experiments debunk quantum mechanics, the particle model. We have to get rid of the particle model. No, they just created more principles to accommodate the particle. So you got the principle of complementary duality. You have the principle of uncertainty and so on. So they included principles to accommodate the particle instead of getting rid of the particle. Okay, so what can I say about Mr. Weigand? Well, He's like a chess player, grandmaster. He enjoys playing chess, does that every day. Is that good for anything? Well, no, it's entertainment. I mean, you go in there, you play chess every morning, and you love it. And you play all these different games. Say, oh boy, it's beautiful. What a beautiful move I made here today. One that I came up with, and so on. And it's very, it's you get enthusiastic about it because you can discover movements of your pawns and your rooks and so on. And you like those moves. You say, oh, that was smart. Look, I did it this way instead of doing it that way. So you learn, and it's great. What does chess produce? It produces absolutely nothing other than entertainment, especially for the guy who, is a grandmaster who does this every day. Are you going to support that? You're going to say, well, I'm going to support chess all over the world. No, that's something that they should do because it's like a game for them and they love it, and that's great. No problem. Just do your thing over there, but don't tell me that because you play chess, you know physics or that you can understand how this universe works. And Mr. Weigand is no different. He enjoys doing his calculations, his math, his derivatives and integrals. He loves that stuff. He's applying it to what? To what soul's going to heaven, to the volume of heaven. Is that what he's applying it to? We don't care. If he believes in that stuff, well, he should found a church and not use government funds to do his stuff, unless he can justify that that has something to do with science and with physics. Right now, we're paying this fellow, and many others like him. Okay, I'm picking on him, but he's representative of a lot of people out there, that you're paying their salaries, you're paying their education, you're paying directly or indirectly also for them to go into conferences and so on. What do these people produce? They're producing equations. What are those equations on? On gravitons, which they cannot justify. We're talking about a mathematical concept, not a physical object out there. You cannot explain with gravitons why the pen falls to the floor. Or they apply it to general relativity, warp space, which again, there is no such monster as warp space, especially there's no such monster as warp time. Because they're saying that, you're warping space-time. That means you're warping time. Gravity warps time. And that's the reason the Earth doesn't fly out of the solar system. So, yeah, I got to take that literally because you're telling me that the Earth doesn't fly out because there's a warp wall of time that prevents it from leaving the solar system. That's why I got to take it literally. Otherwise, you got to explain why the Earth doesn't fly out of the solar system. You got to give me a physical mechanism. You can't say, well, God works in mysterious ways. Not a good answer in physics. So if Mr. Weigand likes to do calculations, he likes to do his little chess game, he calls it calculations, string theory, whatever he calls it, fine. Do it on your own time, on your own money, and do it in your own club, your own church, your own Sunday school. Don't bring it into physics. It has nothing whatsoever to do with physics. It cannot explain gravity in any way, shape, or form. Never has, never will. And for sure, you're not going to be able to run an experiment to verify your predictions because you're talking about 10-dimensional whatevers, 6 of them which are hidden, maybe curled into one another, as they say. You can barely deal with the 3 dimensions of physics, okay? And then he's dealing with a graviton, which is what? A one-dimensional line? No, one-dimensional, not even one-dimensional. It's just an itinerary they call one-dimensional. He's talking about a number line. This number line shakes, vibrates, and creates a vibrating itinerary. That's what it is. He's vibrating an itinerary. He calls that a particle. With that vibrating itinerary, he plans to produce the force of pull of gravity. No, absolutely nonsense. All of it. 150% of it. None of that survives rationality. And instead of that, he should, I wouldn't mind contributing to his treasury if he would at least go into Quora and answer some of the questions, baby stuff, that people ask, like, what is gravity? How does a magnet attract another? If he could answer those questions, then maybe he's worth his while. Otherwise, he's not. Okay, let's go to the question and answers today. Comments. Here we have our first one. If I can get this thing up here. Okay, a fellow says, if you think energy is a concept, stick your tongue in a light bulb socket, or stand in a nuclear reactor, or just stay out in the sun too long sunbathing. You will quickly change your mind that energy is an abstract idea. Okay, let's find out what the answer to that is. Okay, here we go. How will you determine that energy is either an object or a concept? By sticking your tongue in a socket. I mean, what have you shown with that? You just showed that you got electrocuted, but you don't know what did it. You don't know how it did it. That's the issue. By saying energy, you haven't fixed the problem. All you did was hide the mechanism. You've masked the actual participants. What criteria are you going to use to determine whether energy is an object or a concept? By standing in a nuclear reactor. I mean, you stand there, okay, you get fried or whatever, and what did you determine with that? Did you determine that because what did it? Did you determine that energy is not a concept or that it is an object? For that, you need to define what energy is, and you need to define what an object and a concept are. Once we have these words very well defined, then you can talk sensibly. Then we can say, yeah, energy is a concept or energy is an object. Right now, you can't say it because you don't have a definition. And again, in what way will sunbathing tell you that an energy is either an object or a concept? You need to define these terms, and right now we have no definitions in ordinary speech for these words. And really, we don't have in mathematics either, because that's where ordinary speech, the dictionaries get their definitions. So we don't have a definition for this. I mean, what is energy? The capacity. So is that capacity what fried your tongue? Is the capacity what, when you sunbathe, is that what toasted you and got you all brown? The capacity? What does that mean? What is the mechanism? What do you mean the capacity did it? So you can't say, oh, the capacity did this or the capacity did that. You got to explain the mechanism. And for that, you need objects. And you need to define the terms that you're going to use to make your explanation, to make your physical interpretation. Okay, same fellow. He's got several here. I pulled them all because there's a total misconception on his part on several issues. A charged battery weighs more than a dead battery. Okay, fine. And we transfer nuclear and solar energy into electric all the time. Well, you can't transfer energy until you define what energy is. And if you say the capacity, well, you transfer the capacity. That's like saying, well, you transferred love. What did you transfer? I mean, is energy a physical object? If it is, draw it. Or define the word object otherwise. I mean, an object is that which has shape. Very simple. The tri-field meter measures electric, magnetic, and radio frequency fields. Okay, measures a field. If fields were a concept, we wouldn't be able to measure them. What does it look like? I mean, please draw a field, standalone field, okay, without any other object nearby. Okay, just a field all alone in the universe. That's what we need to see. And hopefully you can do something with that drawing, with all those, whatever you draw, right? And the way we do it in science a little differently, we have, what have you established with this? What can you explain with this trivial description? Because so far all you said that battery weighs more if it's charged. And what do you mean by that? Okay, what caused it to weigh more? And you say, what, is it a ghost that's in there or what? What is this energy thingy? And you transfer the capacity, is that what you transfer when you say we transfer nuclear and solar energy? What did you transfer? And again, the field, what did this field that you measured look like? Please provide a picture, a link will do, of a standalone field. Field, if you look it up, it says a quantity. That's what it is. That's what a what the word field means, a quantity. And so the question is, you measured a quantity. Great. So what did you measure? What do you mean you measured a quantity? I mean, I can measure an elephant and come up with a quantity, but to measure the quantity itself, I don't know. I don't know how you can measure a quantity. Please show us how you do that. Okay, so yeah, there is no physical object called a quantity in physics. Okay, so you need to identify the physical object that you're going to measure. Okay, it's easy to say, oh, I measured a field, I measured energy. Now you got to draw them. You got to draw a picture of energy, a picture of a field, so we know what it is that you measured, what you pulled your what is it, your ruler across, or you timed, or you weighed, or whatever. If you're going to measure something, and you're calling it, saying that it is a something, that it's not a concept, that it's a something, hey, you need to bring it to the conference, put it on the table, and then we know what you are weighing, what you put your measuring tape across. Okay, otherwise we don't know what it is that you measured. They had to be objects. Okay, you can only measure objects. You cannot measure concepts. Not with a ruler, at least, not with a scale, so I don't know how you're going to measure them. What, in abstract mode? Okay, fellow says, what? He said, rope is a concept. Such basic things. These people will get tangled in very simple things. Okay, let's see if a rope is a concept. No, I would say that rope, anywhere in the universe, the word rope always refers to an object. Here and anywhere in the universe, all ropes have shape. An object is that which has shape. So I'm not sure what this gentleman is not understanding. Obviously, if the word rope always refers to a thing, here and in the land of the Klingons and Mars, everywhere in the universe, rope is always an object. So why he says it's a concept, I have no idea. I mean, I always like to say that you can go to the hardware store and ask for a rope, and they'll give you something that you can touch and bring home. And if you say, give me a field, give me an electric field, or give me a magnetic field, or maybe a gravitational field, what will the guy at the hardware store give you? What will he sell you? What will you take home with you? Well, give me a pound of energy. How's that? I mean, you going to take energy with you? I mean, what is it? What are you taking home with you? So no, you can't take home energy. You can't take home a field. You can't take home mass. You can't take home charge. None of those, because those are all concepts. What are you going to take for charge? 1.6 times 10 to the minus 19 coulombs? Is that what you put in your pocket? Yeah, you got to know the difference between an object and a concept. First rule of physics. You can't do physics without an object. Okay, I think this gentleman also continues. He says, what? He says, circle is a concept. He's got it in reverse. He says that rope is a concept and a circle, which is an object, is a concept. Okay, let's find out. Gentleman has to take kindergarten physics. Never went to kindergarten physics, never took his first course in physics. Okay, do you see a shape there? We call it a circle. Looks like that. And obviously it has shape. And an object is that which has shape. It doesn't matter if it's 2D or 3D or whatever. I mean, as far as I know, there's nothing over 3D, nothing below 2D. Every object is 2D or 3D. And this is one of the 2D objects. Okay, it doesn't exist. It has no location. What has location is the paper and the ink, or in this case, I guess the pixels. There's no physical object, standalone object out here that's called a circle. Okay, but it does have shape. Okay, and if you can create this out there in space, like floating around as the only object in the universe, it would have to be a ring. It can't be a circle. Okay, so that is what an object is, that which has shape. So this fellow has to really do his first homework in kindergarten physics, and that's identify what an object and what a concept is. Then we can talk sensibly and know what is an object and what is a concept. We just have to define these terms. That way we know what one is and what the other is. So just fill in the blanks there, okay? Okay, another comment here. I think the last one from this fellow. And he says, liquid has no shape. And then in another context, he says, liquid on the space station takes a sphere shape. Okay, so please stop arguing with yourself, with the guy in the mirror, okay? And figure out if liquid has shape or not. Yeah, liquid has shape. All liquids have shape. Uh, the liquid called beer that I have in my bottle takes on the bottle shape. If I put it in a balloon, it maybe takes a spherical shape. And if I throw it out of the space station into space, it takes this irregular blob shape. It always has shape. So yeah, liquid always has shape. Gas has shape. All gases have shape. They had better because they're made out of atoms. So, they had better have shape. Okay, another comment here, or question. Fellow says, bad move to say complex numbers can't model the real world. Well, model, and model. What are we talking about? Are we talking about physics? We're talking about physics, which is what we do here. We do physics, right? Then, yeah, I don't know if you can model it with any number, with any equation, okay? And you have to know the difference between physics and math. There is no such thing as mathematical physics, okay? That's where the problem is here. When we talk about models, we're talking about physical models. We're talking about models for mechanisms, okay? And so there, you have the models that math has, which is quantitative descriptions, has no place in science. What we have in physics, which is a branch of science, is qualitative explanations. In other words, physical mechanisms, as we call them. Okay? Mechanisms. You need a mechanism. You need to explain how gravity works. You need to explain how light works, magnetism, workings of the atom, electricity, all that. You need to figure out all those invisible things. We figured out all the visible ones. All we have left to do, figure out the invisible ones before humans become extinct. Okay, another fella. He says the following. He says, what is the rope made of? Oh, that was easy. 2 strands. Very easy. 2 threads, 2 strands. Whatever your word you want to put. 2 wires, 2 cables, 2 coaxials. I don't know. Any of those will do. Yeah, it's very simple. Just go to the hardware store and you will find that, like here, 2 strands. Threads, strands, strings, whatever you want to call them. 2 of them twined around. That's what it's made of. That's all ropes. Well, some ropes are made of 3 strands and so on, but the rope I'm referring to is 2 strands, okay? So yeah, 2 strands. That's what a rope is made out of. Okay, but anyways, it's an issue of mereology, and we don't do mereology in science. That's religion. We don't ask, what is the table made of? We have no purpose for that. What we say is, we have to explain something. So we can say, look, with the table, he broke the window. We have an explanation for how the window broke, and we say it was the table. And a guy says, what was the table made out of? Gazillion atoms? I don't know. I didn't ask. I didn't check it. I didn't take it to the hardware store, to the metal worker or whoever. No, I just used the table to break the window. So you asked me, how did the window break? I used the table. What is the relevance of what the table was made out of? Okay? I used the table to explain something. Okay? It's like saying, what is God made of? Well, we don't care about that. We don't care what God is made of. What we care is, how did he create the universe? Tell me the mechanism. Then we can follow you. But to say, oh, but what is God made of? I don't know. Spirit? I don't know. I have no idea what God is made of. Atoms? I don't know. Space is nothing, he says. Yeah, that's the easy part. The tough part is saying, what is nothing? You got to define what nothing is. It's easy to say space is nothing. But see, that's a synonym. Nothing and space are synonyms. You need to define what the word nothing means. Then you can say space is nothing, because space is a synonym. And you can't use either antonyms or synonyms to define either nothing or space. Okay, because a synonym is a circular definition, and antonym is the same thing in reverse. It's just, you can't say nothing is not a thing. No, that's like saying, well, what is a thing? Well, it's not a nothing. Yeah, you can be all day just chasing your tail around. No, no, if you're going to define a word, you can't use antonyms or synonyms. Okay, okay, and I've got the last question here, I think, or comment. Well, it says, what? Says string theory, rope theory. Okay, there are waves that are ropes. There are particles that are twisters, and there are wave particles known as plasmas. No, 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 no way, none of that. All of that is completely unscientific. Okay, so what is the real thing? Is string is not a string, and it's not the same thing as a rope. Okay, string is a 1D line, as I just explained a little while ago, and it's not even a 1D line. It's not even a 1D anything. It's an itinerary, and that's why they call it one-dimensional in mathematics. No, it's not one-dimensional. What they're talking about is an itinerary that is represented by a number line, because the mathematicians are interested in how far a person went along that path. So it's not the path through the forest, it's the locations that you occupied as you went through the path that went through the forest. That's the way you got to look at string theory. So it's not a 1D anything, it's not even a line. And a rope is totally different. Rope is a twined pair of threads. So got nothing to do with string theory. And besides, it's not a rope theory, it's a rope hypothesis. It's again, you got to know the difference between a theory and a hypothesis. Hypothesis is an assumption, and in this case, we have to make an assumption about the invisible mediators that Mother Nature uses to do her magical work out there, gravity, magnetism, light, etc. Okay, are there waves that are ropes? No, wave is not a rope. Okay, twister is not a thing. A twister is a verb, and so is a wave, by the way. Plasma is not a thing. There's no such thing called plasma. Plasma is something in motion. Plasma is ionization of something, okay? And for that, you got to discover what ionization is, and you'll find that it's a verb. It's something that is happening. Okay, so no, we should not confuse verbs with nouns, and that's where you should start. You should figure out the difference between a verb and a noun. Right now, you're having a little bit of trouble there. Okay. With that, I will see you next time. We'll see you then. Bye-bye. Sure.